Welcome to Unit 4.5. Now we are prepared. On our long journey of classifying crystal structures, we are now ready for climbing up the ultimate step upwards to reach, finally, the space groups. If we consider translational symmetry only, the repeating lattices, we saw that there are 14 different possibilities, the 14 Bravais lattices. If we restrict symmetry considerations to macroscopic crystalline objects, discounting their potentially additional internal translational symmetry, then we end up with 32 crystal classes, describing their different kinds of outer shapes. And if we now combine all these symmetry elements with pure translations of the lattice and the two symmetry elements with translational components, namely screw axes and glide planes, then one can show that 230 different symmetrical arrangements in 3 dimensions are possible. This work was done in 1891, independently from each other and almost simultaneously by the two scientists Schönflies from Germany and Fedorov from Russia. The number of possible types of symmetry is, of course, dependent on the dimensionality of the space we consider. On the one hand, 230 sounds relatively large, and it is likely arduous to learn them all, to work with these, and so on. So you might ask, why do we not live in a two-dimensional world? Then we would have to learn only the 17 plane groups. On the other hand, we can be lucky that we do not live in a 4, 5, or 6-dimensional world, because then we would have to struggle with 5,000, 220,000, or even 29 million space groups. Okay, before we will have a detailed look in the forthcoming units at some of the space groups and how to learn to read in this book the international tables, let's first define what a space group is and how to read their symbols. A space group can be relatively simply defined as a set of symmetry elements, together with their respective symmetry operations, which completely describe the spatial arrangement of a 3-dimensional periodic pattern, nothing more. The nomenclature of space groups is very similar to that of wallpaper groups we discussed in Unit 3.7. In principle, the name consists of 4 symbols. We see here an example, PCA21, which belongs to the orthorhombic crystal system. The first symbol indicates always the Bravais type of the lattice. This means the type of centering, which can be P for primitive, I for body-centered, C in the case of base-centered cells, or F as face-centered. The next 3 symbols specify 3 symmetry elements with respect to 3 given viewing directions. Here, in this example, we have first a glide plane C. Mirrors and glide planes are always given perpendicular to the specified direction. In the orthorhombic crystal system, the first viewing direction is along A. Don't be confused with the A and C. A is the direction of the crystallographic coordinate system where we can find the symmetry element when we look along this A-axis, and C is the symmetry element, a glide plane whose translational component is along the C direction. At the second position, there's a glide plane A specified. The second viewing direction in the orthorhombic system is along B. And finally, there is a 2-1 screw axis which is running parallel to the third viewing direction, and this is along the C direction. Axes of rotations and screw axes are always specified parallel to the respective viewing direction. Okay, you might ask, are 3 symmetry elements sufficient to describe the full symmetry of a given crystal in this space group? Couldn't there be more than 3? Well, you're right, there are space groups in which there are indeed 8, 16, or even 48 symmetry elements. How can this be? Well, these 3 symmetry elements are the so-called generators, and this means that not all of the symmetry elements are given, but only a set of symmetry elements from which all other symmetry elements that might be present too can be derived. For instance, you know that two perpendicular mirror planes automatically generate a twofold axis of rotation. And there are many more of such relations. So indeed, 3 symmetry elements are sufficient. The next thing which has to be clarified are these viewing directions. Here in the orthorhombic crystal system, everything is easy. The viewing directions are along A, along B, and along C. Unfortunately, this is only valid for the orthorhombic system. These directions differ from crystal system to crystal system, and you simply have to memorize these. They are given as follows. In the triclinic crystal system, there is no such specific viewing direction. Why? Well, because in the triclinic system, there can be maximum a center of inversion, which has no direction. In the monoclinic system, symmetry elements, apart from this center of inversion, can be present in only one specified direction, and this direction is chosen by convention. The international standard has been set as the B direction. However, in some countries of Eastern Europe, the C direction is preferred. But if someone chooses this non-conventional setting, this always has to be explicitly stated. For the tetragonal, trigonal, and hexagonal crystal system, the rotational axis of highest order is by definition parallel to the C-axis. The second viewing direction is for all these 3 systems A. But the third viewing direction is not the remaining crystallographic axis, namely B. Why? Because of this rule of thumb, we should choose directions in which we find something new. This means symmetry elements which were not already given by the other directions. Remember, for these crystal systems, the A and B axes are identical due to symmetry reasons. This means if we look first along the A direction and find a mirror plane, then we must find a mirror plane also if we looked along the B direction. But this is no new information. Therefore, we choose a different direction. They are specified here for the 3 systems by these numbers, whereby these directions are always perpendicular to the respective lattice planes of these indices. The direction 110, for instance, is perpendicular to the face diagonal, and 111 is the direction perpendicular to the space diagonal. Okay, before we will have a look at a first concrete space group in detail, I would like to shine some light on the relationship between the 3 categories space group, point group, and finally crystal system. And to be able to do this, we have to look first if and how it is possible to deduce the crystallographic point group from the space group. There is a very simple algorithm for that task. We have to be aware of the following fact. A point group specifies the symmetry of macroscopic objects, or finite objects, and this simply means that such objects lack any translational symmetry. And therefore, we can first leave out the Bravais tab of the lattice, because a macroscopic object has no lattice. And we remember, also any other symmetry element with a translational component describes internal symmetry. Therefore, second, any symmetry element with a translational component has to be converted into the respective symmetry element without the translational part. Meaning that we have to convert A, glide planes into simple mirror planes, and B, screw axes into simple rotational axes. And what about the symmetry elements without translational components? They already describe point symmetry, so they simply remain unchanged. Let's practice this with one example. A crystal may belong to the space group P to 1 over n. So, what is its crystal class? Well, we left out P, then the 2-1 screw axis has to be converted into a pure rotational axis of the order 2, and finally the glide plane n becomes a simple mirror plane. Altogether 2 over m. Isn't this simple? Great. But now back to the mentioned relationship between the 3 categories space group, point group, and crystal system. Assume we have a crystal lattice like this shown here, which should belong to the tetragonal crystal system. Now we have to look for symmetry elements subsequently along these viewing directions, C, A, and 1, 1, 0, the phase diagonal. Along the C direction we see, of course, the fourfold axis of rotation. And we find another symmetry element along the same direction. Yes, correct, a mirror plane perpendicular to that axis. Along the A direction we come across a mirror plane. And along the phase diagonal there's another mirror plane. As it looks like a primitive unit cell, we have lattice points only at the corners, so this crystal must belong to the space group P4 over M, M, M. And what is its crystal class, according to the algorithm we just learned? Yes, it is 4 over M, M, M. But now let's have a look at a crystal with a different motif. Here, instead of atoms or spheres, tetragonal pyramids are present. And additionally, this motif is present also in the center of the cell. Can you derive the space group and the crystal class? Think for a while. Pause the video for a moment if you want. Exactly, one mirror plane is gone, so to say, and we changed the Bravais lattice type from a primitive to a body-centered one. So the space group is I4MM. And the crystal class is then, of course, 4MM. A last example. Look at this cell. We have the same overall motif as in the case before, but what is different? Right, this is no longer a body-centered cell. For this, the motif in the center should have been an identical orientation, but here it shows a different one. So, P4MN and 4MM is the right classification. This was rather a long unit. Sorry for that, but I simply couldn't decide where to break. In the next unit, we will have a look inside the most important book of every crystallographer's affairs, the so-called international tables. See you soon.